So, an IP address consists of two main portions. We have the network address portion, also known as the network ID. This identifies a specific network. Routers maintain routing tables that contain network addresses. It's important to realize that routers build their routing tables based on the network address and not on the host address. So they do not route packets from one interface to another interface based on IP addresses. They do their routing based on network addresses. So they will look at the destination IP address in a packet and match that to a network address in their routing table to determine how traffic is routed. So an IP address consists of the network portion as well as the host portion, which is also called the host ID. This identifies a specific endpoint on a network, such as a server, a printer, a PC, an iPhone, an iPad, or some other type of device, including IP phones. These are essentially the devices that need to communicate with each other. So a PC may be communicating with a server. You may be using your iPad to read the news. So you'd be surfing to CNN.com or USAtoday.com or the BBC. So your iPad is sending traffic to that server and the server is returning traffic to your iPad. So the iPad and the server will have a TCP session established at layer 4, but for the iPad to communicate with the server, routers need to route traffic to the server and back again. So here's an analogy to explain network and host. In cities throughout the world, you have streets. So as an example, we have Oxford Street. On the street, we have multiple houses or multiple offices. But in my example, let's assume we have houses on the street. Each house has an individual house number. So we have, in this example, 1 Oxford Street, 2 Oxford Street, 3 Oxford Street, 4 Oxford Street, 5 Oxford Street, and so forth and so on. Each house number uniquely identifies that specific house on this street. Now, you wouldn't have 2 houses with the same number on the same street. That would be very confusing, because perhaps you want to meet your friends, the Joneses, at number 1 Oxford Street. But you may end up spending your day with a totally different group of people if you have 2 houses with the same number. In this example, we have 2 number 1 Oxford Street houses. Which house is the correct house? Now, that's not desirable. When you go to 1 Oxford Street, you want to make sure that you're going to the right house to meet your friends rather than going to some other house. And hence, house numbers need to be unique on a street, in a city, in the world. Now, continuing with our analogy, when working out how to get to a remote destination in the physical world, let's say you want to go to Oxford Street in London in the UK, and you've never been there before. You may use a mapping technology such as Google Maps to find out how to get to that specific street. Now, when you're doing this, you don't look at individual house numbers, but rather look at street names to determine your way to get to that destination. So if you're in a different part of London, you may use the street name to work out how to get from your current street to Oxford Street. And when you get to the destination street, then you're able to look at house numbers to determine which house number to go to. Technologies such as Google Maps are obviously really intelligent and know the house numbers and will guide you to the right part of the street. But for this analogy, think of how routers route. They will route traffic to a destination network, and when traffic gets to that destination network, then house numbers are used or IP addresses are used to determine which host to forward the traffic to. Now, in a similar way, the network address, in this case 10.1.1.0, identifies a specific network somewhere in the world. Host addresses such as 1, in this example, identify individual devices on that network. So 1 identifies this PC on network 10.1.1.0. Each device on this network has a unique number. So in this example, we have 5 unique devices, in the same way that in our previous analogy, we had 5 houses on Oxford Street. Now, in the same way, you wouldn't configure multiple PCs or multiple devices with the same IP address as that would cause confusion and conflicts. So as an example, if another device wants to communicate with 10.1.1.1, which PC would it send the traffic to? If PC5 wants to communicate with this host, 10.1.1.1, there are two hosts with the same IP address. Which device should PC5 communicate with? So, devices on a network or subnet, which we'll talk more about in a moment, have a unique IP address in the same way that a house has a unique house number on a specific street. So in the same way that we use street names when going from A to B, routers look at network addresses to determine how to get to a remote destination. Other protocols such as Address Resolution Protocol or ARP are used to find the house number or host number for a host on a specific street or network. So in this analogy, we're going from Queen Anne Street to Oxford Street, and we would use street names for our directions as per this example. But once we get to the street, in this case Oxford Street, we would look for the specific house by looking at house numbers in the physical world, or in the network world, we would use a protocol such as ARP to find the specific host on that network. Routers do not make routing decisions based on IP addresses, they make it based on network addresses. A router's routing table is not populated with IP addresses, it's populated with network addresses. The destination IP address in a packet is then matched to the routing table, populated with network addresses, and then a determination is made to decide out of which port or interface on the router the packet should be forwarded. So once again, the format of an IP address, in this case IPv4, is a 32-bit binary number. It's divided into 4 parts, or 4 octets, which are 8 bits or 1 byte in size. So an IP address could be written as follows, in binary in dotted decimal notation, or it could be written as follows, in dotted decimal notation. So just to summarize, it's a 4-byte number or 32-bit number, typically written in dotted decimal notation, but be aware that it's actually a binary address of 32 bits. Please refer to the binary videos if you're not sure about the formatting or conversion of binary to decimal and back again. An octet is 8 binary bits or 1 byte. 1 byte equates to 8 binary bits. So an IPv4 address consists of 4 octets, such as x.x.x.x, where x is an octet or 8 bits or 1 byte. Now using our street analogy again, it's possible to have the same house number on different streets. So house 1 could be on Oxford Street as well as Cambridge Street. House number 1 should just not appear twice on the same street, but number 1 is permitted on different streets. In the same way here, it's possible to have number 1 on network 10.1.1.0/24 as well as number 1 on network 12.1.1.0/24. The same number can appear on different networks. I'll explain the /24 in a moment when we discuss network masks, but in this example we have network 10.1.1.0 and 12.1.1.0, and it's possible to have multiple devices with the host portion of the IP address set to 1. The same host portion can appear twice, as in this example, or many times in a network or the internet, as long as the network portion is different. Now, one thing you'll learn about networking is that things are constantly changing. Address classes, or classful networks, were used in the internet from 1981 until the introduction of classless interdomain routing in 1993, which is commonly known as CIDR or CIDR. Now, prior to 1993, address classes were used to divide the IPv4 address space into 5 address classes. The 3 that we're going to concentrate on here are class A, B, and C, which are used for unicast traffic. Class D is used for multicast, and Class E is reserved for future or experimental purposes. Address classes have been superseded in IPv6. IPv6 does not use address classes, and in IPv4, address classes have been replaced with CIDR. So the different classes of addresses, A, B, and C, were used to accommodate different sizes of networks, which aided in the classification of those networks. So as an example, a class-full A address supports about 16 million IP addresses. So once again, we had class A, B, and C. These have been replaced or superseded by CIDR or CIDR, and address classes such as A, B, and C were determined and then allocated by the IANA or Internet Assigned Numbers Authority. This format is not used entirely in its original format today. Here's an entry on Wikipedia showing the list of Class A addresses. So each Class A address has approximately 16 million IP addresses, and if we scroll down the list, we can see various examples. AT&T have 12, Xerox 13, HP 15, DEC 16. So 15 and 16 are now owned by HP. Apple have 17, MIT 18, Ford 19, and so forth and so on. So notice, as an example, Apple own 17.0.0.0/8. Apple have 16 odd million public IP addresses that are part of the Class A address. So in the original IP address format, a Class A address consists of 8 network bits and 24 host bits. Hence it's written as /8, denoting 8 network bits. Now this was fine when the internet was small, but it quickly became a limiting factor, and thus multiple addresses were introduced with different size network portions. Hence we have Class A, Class B, and Class C addresses. Please note, once again, that class full addresses were replaced in 1993 with classless interdomain routing, or CIDR, also called CIDR. However, you may still come across commands that use the class-full address format. An example of that is the network command within routing protocols. So as an example, if you use the network command on a RIP routing process, the command is written in a class-full format. It's also worth knowing a bit of the history and understanding why we have problems with the lack of IP addressing today. Hence, it's worth your learning about classful addresses for completeness. The breaking up of addresses was originally used to try and save or conserve IP addresses, but did not work in its original format, and thus was expanded and changed by CIDR. I'll explain CIDR in a moment, but let's first look at the various address classes in more detail.